Welcome back to INST 314, Statistics for Information Science, with your host, Shawn Janzen. Now we're going to go ahead and take our talk about the Z and T one-sample hypothesis testing, and we're going to apply it into a problem. We're going to show you how the formula works in a current example and do its interpretations. So let's go ahead and learn how to conduct a one-sample means test. Now this means test, I do want to just, by the way, point out, was taken from heavily with an example out of the Healy 2009 book, Statistics, a Tool for Social Research. And we're going to talk about a grade inflation problem. Now in our grade inflation problem here, we have an education department at a university, and it has been accused of grade inflation, so that education majors have much higher GPAs than the other students in general. Now, in order to do this, we have to look at the GPAs of all education majors and compare them to the GPAs of all the students at the university. Now, of course, there are thousands of education majors, too many for us to interview. So how can we dispute those investigated without interviewing all of the investigation majors? We're going to use a hypothesis test for means. So let's go ahead and check through our steps, formulate the hypotheses, prepare and check the conditions, set our alpha level, check the Z or T score using the formula, Z equals x bar minus mu divided by standard deviation, which is divided by square root of n, calculate a p-value and interpret the results. So let's see what we know so far. The average GPA for all students at this university is 2.70. This value is a parameter, so we're going to set mu equal to 2.70. Maybe we can say that the university's registrar provided this for us, and of course they're not going to give us the GPAs for all students in the university for privacy reasons, but they're willing to share with us the population mean. And we go ahead and get from a sample of students that we went and collected information from, that we went and interviewed 117 education majors, and of them we found that the X bar, or the average of that sample, is 3.00 with a standard deviation of 0.70. Now let's go ahead and put this into forms of hypotheses and what it is that we're looking at and what it is we're expecting to see. So we want to see if there's a difference between the parameter 2.70 and the sample statistic 3.00. It looks like, just by the numbers, that education majors do have higher GPAs, but this is just a sample and might not be representative of all education majors. So either the sample mean that we have, 3.00, is actually same as the population, 2.70, and the difference that we're seeing, it's trivial and just due to random chance alone, or the difference we're seeing is significant and real, that education majors are indeed different from all other students at the university. So let's go ahead and construct some hypotheses. The null hypothesis, this is the one that we're saying that there's no difference between them. This difference is just random chance. And so the alternative is going to say the difference is real. It's always going to contradict the null hypotheses. Only one of these can be true. Which one, we're going to use the test to help us determine. So we can construct the null to say that mu equals 2.7, that the sample of 117 comes from a population that has a GPA equal to 2.7, and that any differences we're seeing between 2.7 and 3.0 is trivial and caused by random chance. This is the assumption that we start with as true. The alternative is that the average is not 2.7. So in this case, we're doing a two-tailed version. We're not saying if the education major is going to be higher or lower. We just want to see if they're different. So we're then saying that the sample of 117 comes from a population that does not have a GPA of 2.7. That population would be the education majors. So we're saying that the difference between the 2.7 and 3.0 reflects an actual difference between the education majors and the other students. We go ahead and prepare our data, and we say that this is random sampling. We're going to assume that the sample we obtained is following the rules of EPSEM, that's the equal probability selection method, and so that they're saying they're random and independent. Okay? And if it was actually or not is beyond the scope of our small example here, but we're going to assume that if we did this and we did this properly, we made sure that our sample was random. Now, the GPAs, this is an interval ratio type measure, so the GPA is appropriate for doing Z's and T testing on, and I have a histogram here to kind of show us what the GPA would look like, and it looks normally distributed. Some of them are high, some of them are low, with the bulk of them in between. Now, when we talk about our sampling distribution, we can go ahead and say that it is normal in shape. This is a large sample and is larger than 100, and less than 10% of all of the students at the university, even those that are in question. The sample population, standard deviation, the population standard deviation is currently unknown. So, what is it that we're going to use? Well, we could say that we're going to use the sampling distribution z because n is greater than 30. But I'm also going to show you the t as we go through this because we don't know the population standard deviation, so a case could be made for using the t distribution as well. We're going to set our alpha at 0.05, where alpha is our maximum that we're willing to risk and our benchmark for saying if it is rare or unlikely to occur. Now, the critical region that we need to know for this, and we covered this in the previous video on critical regions, that the z-score of a two-tailed test with an alpha of 0.05 corresponds to plus and minus 1.96. So if we get a z or a t score that is larger than our critical region, we will go ahead and reject the null hypothesis. Let's go ahead and do the math here. Now, we have mu of 2.7, x bar of 3.0, standard deviation S of 0.7, and n of 117. Plugging all of those in, if we did this with the z-score, we get a z-score of 4.63. If we do the t version, the math is exactly the same. We still get a 4.63. However, we include a degree of freedom where n minus 1, so the degree of freedom is 116. Let's go ahead and take this into the next step. Now, we said before that our z-score of 1.96 holds, but we also need a critical value for t if we're going to do the comparison for t. So looking at the t table, we're doing a two-tail, so we move over to the alpha 0.05 column for two tails, and then we look down to where we find the t-score closest to 116 degrees of freedom. Now our t-table stops at 100, and the next step is 1,000, and we'll notice that the difference between these scores is different, but we're going to compare it closest to 100. That's closest to our degrees of freedom of 116. Moving across to intersect, I get a t critical value of 1.984. This is very close to our z critical value of 1.96. Remember, I said that z and t approximate each other when the sample size of t becomes large. So let's go ahead and take that and figure out where we're going to be. And so let's go ahead and make our interpretation. The z critical value was 1.96. The t critical value was 1.98, very close to each other, and the t scores that we obtained for both z and t is 4.63. So can we reject, or do we fail to reject, the null? I have a distribution for us here where the red shaded regions is the z critical region, and I plotted a red bar out where our z score was. So 4.96 is far off into the tail, past 1.96. Go ahead and think about this for a moment. I'll wait. Now what we're going to find is that z-score obtained is much larger than the z-critical region, and since it falls into the critical region, we reject the null hypothesis, which says if the null were true, a sample outcome of 3 would be extremely unlikely. How do we go ahead and conclude this? Well, by rejecting the null, we say that there is some evidence for the null to exist with the alternative. The education majors have a GPA that is significantly different from the general body. Now, what we go ahead and do with this, that's a topic for a different video. That could be a delicate situation that we need to then talk to those running the education department and find out why that we're finding these significant differences, or if perhaps we may have committed a type 1 error and if another sample is going to be needed to prove this. So, but that would be, like I said, a topic for another video. But let's go ahead and confirm our results using p-values. So switching our gears into R, we're going to go ahead and set the z-score, and we knew the z-score that we obtained was 4.63, but in this case I'm going to go ahead and just put all this into an object that I'm calling score. So I've done some math and I've assigned it to score, and then I'm going to find the p-value. And note, I'm multiplying the p-value by 2 to get the two-tail test result. So I use the p-norm function, and I'm plugging in the score. If you've already calculated the z-score like we have with 4.63, you can just put in 4.63 here. But using score, that's going to be more accurate because it's going to carry out the decimals much farther than we did. Comma, lower tail equals false, so it's going to find the p-value of that z-score out in the left tail. I'm sorry, right tail because it's false. Multiplying that by 2, and you're going to go ahead and generate our two-tail test score. Now, if we were to do this for a t-test, it's similar, but instead of doing p-norm, we use pt, probability for t. We put in the score, you put in the degrees of freedom. I could put in 116. In this case, I just did 117 minus 1. It'll calculate out. Again, lower tail equals f for false, multiply by 2, and we get the p-values. Now, the p-value for z was 0.5036, and t was 0.5094. Both of these are extremely small values, very small compared to our alpha of 0.05, so we are confirming our results from the t-critical values that we found, which would make sense since critical values and p-values should match each other in tandem for your particular results. But that's just how you can go ahead and do it in R as well.